So for question 1 of this exercise, what we're asked to do is find the chemical formula for iron 3 oxide, and the simplest way to do this is to use the SVSDF method. So SVSDF, and what that stands for is symbol, so you show the symbols of both elements that you're using, or complex ions, V for valency, S for swap, D for divide, and F for formula. So in this case we've got iron and oxygen, two elements, so the symbol for iron is Fe and the symbol for oxygen is O. The valency is how many bonds each of these atoms can form. Iron is a transition metal, so you're always going to be told the valency of the iron. In this case it's 3, we've got 3 here in Roman numerals, so the valency is 3 and the valency of oxygen is 2. We swap those numbers over, and that gives us 2 and 3. We can't divide those numbers any further, we can't simplify them any further, we can't take out a common factor, so we leave the numbers 2 and 3 as they are. So that means we have 2 irons for every 3 oxygens, so we get Fe2O3. In question 2, we're asked about the final stage of the blast furnace, where iron oxide undergoes a reaction with carbon monoxide to produce iron and carbon dioxide. So that's the final stage of the blast furnace, where the iron is being extracted. So what we're looking at is particularly the iron, what's happening to the iron in this final stage of the process. So we have Fe2O3 on the left hand side, and that's becoming Fe on the right hand side. So we're starting off with iron in an ionic compound, and we're ending with iron as a single element on its own. So the iron has been extracted. If we write the ionic formula for iron oxide, we're able to see more accurately what's happening to the iron in terms of its charge. So iron oxide, which we worked at the formula of in the last question, is Fe2O3. If we show the charges in there, it's an iron 3 ion, and oxygen's got a valency and a charge of 2 minus, and we have 3 of them. Okay, so we're going from Fe3 plus now on the left hand side to Fe, and we're not really particularly bothered about the oxygen. We can remove the oxygen from this because we're just asked about the iron, and if we remove the oxygen we can remove this too as well. So what do we have then? We have Fe3 plus going to Fe. How do we get from Fe3 plus, which is a 3 plus ion, to an overall neutral Fe atom? The way we do that is we need to get that 3 plus charge and add 3 electrons, so we get to the same number of protons and electrons. We need to add 3 electrons. So we have an ion gaining electrons to become an atom. So what we end up with here is a reduction reaction. Reduction is gain of electrons. Okay. In question 3, we have a calculation from balanced equation question. So what we have at the start is 191 grams of magnesium chloride. This is 191 grams of magnesium chloride, and we're asked to work out the mass of magnesium that is produced when magnesium chloride undergoes electrolysis to split up the compound into its 2 elements. So we're asked to work out magnesium. So we can forget about the chlorine because that's not actually part of what we've been asked. So let's show a ratio, MgCl2 to Mg. We can see it's a 1:1 ratio. So what we want to do first of all is work out what mass 1 mole of each of these substances would have. So i.e. work out the gram formula mass. So MgCl2, Mg is 24.5, chlorine is 35.5, multiply that by 2, which is 71. So overall we would have a GFM for magnesium chloride of 95.5 grams. So we're starting off, if we look at this theoretically, if we started off with 1 mole, that would be 95.5 grams of magnesium chloride, and that's producing 24.5 grams of magnesium. But how much are we asked about in the question? How much do we actually start with? We actually start with 191 grams. So this is our actual mass. So if we started with 191 grams of magnesium chloride, how much magnesium are we going to produce? So how do we get from 95.5 to 191? So this is a simple question in terms of the calculation we have to do, because we can go straight from our theoretical mass to our actual mass by multiplying it by 2. So 95.5 multiplied by 2 gives you 191, and if we do that on one side, we have to do the same on the other side. Multiply by 2, 24.5, multiplied by 2 is 49 grams, and that is our answer. Question 4, we're asked to work out the mass of mercury that is produced when we start with 43.3 grams of mercury oxide. So we're starting with mercury oxide and we're asked to calculate the mass of mercury produced in the reaction. So I've ticked the two substances from the balanced equation that we're concerned about. That means that we can ignore the oxygen. And once we've done that, what we can do is we can show just those two substances as a ratio. Your teacher may put an arrow in the place of this colon here. So what you may see is something like this. And that's absolutely fine as well. So what we want to do now is look at the ratio. So it's a 2 to 2 ratio, and with a 2 to 2 ratio we can cancel that down to a 1 to 1 ratio. So 1 mole of mercury oxide will produce 1 mole of mercury. So let's now work at the GFM of mercury oxide and of mercury, HgO. So an atom of mercury has a relative atomic mass of 200.5 and oxygen is 16, and if we add them together we get 216.5 grams. So that's our GFM, i.e. that's what mass 1 mole would be theoretically. And then Hg, mercury we've already established is 200.5. So that's how much we would have if 1 mole was reacting to produce 1 mole. But what we actually have is 43.3 grams. So how much mercury would be produced if we started with 43.3 grams of mercury oxide? So the way we get from 216.5 down to 43.3 is that we need to divide it by 5. Again, sometimes a calculation requires you to go to 1 gram first and then to multiply by the desired mass, but in this case we can see that 216.5 can be simply divided by 5 to get 43.3. So that gives us an answer of 40.1 grams. Question 5, calculate the mass of zinc oxide required to produce 6.55 grams of zinc. So we are kind of working backwards now. As opposed to working out the mass of a product that we produced, we are working out the mass of reactant that is required to produce a certain mass, and that is 6.55 grams of zinc. So let's keep it simple. Let's identify the substances from the balanced equation that we're concerned with, and that will let us eliminate the substances that we're kind of just going to ignore. So zinc oxide and zinc, which means you can ignore the carbon and carbon monoxide. So then let's write a ratio. Zinc oxide to zinc, it's a 1 to 1 ratio. What we can then do is work out the GFM, as we've seen before. GFM of both. So zinc oxide, zinc has a relative atomic mass of 65.5 and oxygen 16. If we add them together we get 81.5 grams. So the GFM of zinc oxide is 81.5 grams, and zinc we've established is 65.5 grams. So now we have the mass of 1 mole. Let's think about our next step. Our next step is that we need to get to 6.55 grams of zinc. So we're going to take down the right hand side now. We're going to try and get this side here down to the mass that we're given in the question. So how do we get from 65.5 down to 6.55 grams? Sorry, that's a puppy playing with a dog toy. So how do we get from 65.5 down to 6.55 grams? What we have to do is divide by 10. So if we divide by 10 on one side, then we also divide by 10 on the other side, which gives us 8.15 grams. And that there is our final answer. In question 6, we're asked to work out the percentage by mass of mercury in cinnabar. So cinnabar is a compound containing mercury and sulfur. It's mercury sulfide. So the first thing we want to do is work out the gram formula mass of mercury sulfide. So mercury has a relative atomic mass of 200.5 and sulfur is 32. So we add them together, we get 232.5 grams. So that is our overall mass of that compound. It's the GFM. If we want to know the percentage of mercury in this compound, the percentage by mass, what we do is we take the mass of mercury, which is 200.5, we divide it by 232.5, which is the GFM, the total mass of the compound, and we multiply it by 100 to figure out the percentage, and that gives us an answer of 86%, rounded to the nearest whole number. In question 7, we're asked to work out the percentage by mass of lead in lead 2 sulfide, and we're given the formula of that as well. So PbS, the mass of a lead atom is 207, and the mass of a sulfur atom is 32. So this is a very similar question to one we just saw previously. If we add those numbers together, you get 239 grams. So that is our GFM. So to work out the percentage of lead in lead 2 sulfide, we take the mass of lead, which is 207, we divide that by the GFM, which is 239, and we multiply by 100, which gives us a percentage of 87. So 87% of lead sulfide by mass is lead. Question 8, paint containing red lead was used to protect steel from rusting. Calculate the percentage of lead in red lead, which is Pb3O4. So first thing we're going to do, as we've done before, is work out the GFM of red lead. So lead has a mass of 207, we multiply that by 3 because there's 3 atoms in the compound, which gives us 621. Oxygen has a mass of 16, which we're going to multiply by 4 because that's how many atoms in the compound, which gives you 64. And if we add those numbers together, we end up with 685 grams. So 685 grams is again our GFM, gram formula mass. To work out the percentage of lead, this time we're going to take the total mass of lead and divide it by the GFM. The total mass isn't just for one lead atom. In this case we've got 3 lead atoms, so we have to take that into account. So we're going to do 621 divided by 685 multiplied by 100, which gives us 91%. In question 9, we're asked to do something quite similar to what we've done before, but in this case we're working out the percentage composition. So what that entails is working out the percentage of each individual element within the compound. So here we've only got 2 elements. We've got C8H8. What a few people I've seen did is they immediately saw that there was 8 carbons and 8 hydrogens, so they said, well, it's a 50-50 split there of carbons and hydrogens. But when we're working out percentage composition, we have to take into account the relative atomic mass, and the relative atomic mass of carbon is much higher than hydrogen. So carbon is much heavier. 8 atoms of carbon is much heavier than 8 atoms of hydrogen. So we need to take that into account, and the way we do that is first we work out the GFM. So we'll do 12 times 8 and then 1 times 8. That's 96. That's 8. If we add those numbers together, we get a GFM of 104 grams. So the percentage of carbon is the mass of carbon in the compound divided by the GFM, so that's 96 divided by 104, and then the percentage of hydrogen is the mass of hydrogen in the compound, which is 8 divided by the GFM, which is 104. Multiply both those numbers by 100. So you get 92.3%. and 7.7%. So the answer there is D. Okay, question 10, doing the same as what we did in question 9, but this is a trickier question, probably the trickiest question of the whole quiz. So what we have to do is work out the gram formula mass of calcium phosphate first and foremost. So Ca3, open bracket, PO4, close bracket 2. So what people may have tripped up on is ensuring that the correct number of atoms were accounted for. For example, we have here 3 calcium atoms. So that's 40, which is the mass of 1 calcium atom, multiplied by 3. We've got 1 phosphorus atom within the bracket, but we're multiplying that whole bracket by 2. So we end up with 2 phosphorus atoms, which is 31 times 2, so that's 62 grams. And you've got 4 oxygen atoms within the bracket, but we're multiplying that bracket by 2, as was stated before. So we need to do 16 multiplied by 4 times 2 is 8, multiplied by 8, which gives you 128. So if we add those numbers up, 120 plus 62 plus 128 gives you a GFM of 310 grams. So to work out the percentage of calcium, percentage of phosphorus, and percentage of oxygen, we're going to take the mass of each of those elements within the compound and divide it by the total mass of the compound. So we've got 120 over 310, 62 over 310, and 128 over 310. Multiply them all by 100 to put it into percentage. And what you end up with is 38.7% calcium, 20% exactly of phosphorus, and then 41.3% oxygen. So the answer there is B.